Okay, let's look at two games. The first game is advertising game. Suppose we have two firms, A and B, and they are considered whether to advertise or not. If if both them not advertise, then the payoff, the profit, B can make $2,000 or whatever unit it is. A can make 10. If B advertise, A not, B's profit will increase, and A's profit would decrease to 6. Similarly, if A advertise, B not advertise, B's profit decreased to 0 and A increased to 15. If both of them advertise, then A's profit is 10, B is 5. Okay, what is the outcome of these games? How can we predict the outcome for these games? First, let's check dominant strategy. Actually, we can find that A has a dominant strategy of advertise. So if B advertise, A will advertise. If B not advertise, A will also not advertise. If B not advertise, A will also advertise. So no matter what B does, A will always advertise. For B, if A advertise, B will advertise. If A not advertise, B will still advertise. So B also has a dominant strategy of advertise. So actually, advertise is a dominant strategy equilibrium. And this dominant strategy equilibrium is also a large equilibrium. Okay, we can check this. Okay, given that B advertise, will A deviate from advertise to not advertise? So deviation will decrease the pair from 10 to 6. So the answer is no. Given that A advertise, will B deviate from advertise to not advertise? No, because deviation will decrease the pair from 5 to 0. So the answer is that given the other players' strategy, indeed, nobody has an incentive to deviate. So indeed, this is also large equilibrium. And this large equilibrium is actually unique. You can check that the other cells, they are not large equilibriums. This is easy to see because we know that advertise is the dominant strategy of both players. Okay, let's advertising games. Let's look at second game, firm entry game. So suppose we have two firms again, A and B, and B is an incumbent. It's the firms that's already in the market, and A is considering whether to enter or not. And so B is faced with A's potential entry into the market, and B is going to say straight, say I'm going to cut price or not. So B has two actions: whether to cut price, compete with A, or not. Okay, if A stay out and B not the incumbent not cutting price, so B's monopoly profit is 50. And A's payoff profit 0. So if A stayed out, and if B cut price and A stayed out, and then the profit drop to 20. If A enter and B cut price, so there's a strong competition, so the profit for B is 10, and in such cases A actually is going to make loss. If A enter the market and B not cutting price, A can make 25, and B profits 25. They share the profit, suppose. All right, what's the outcome of these entry games? Let's check for large equilibriums. You can check that this is not large equilibrium. A enter the market, B cut price, because given A enters, B will deviate. Given that A enter the market, B will deviate from cut to no cut, because deviation will increase its profit from 10 to 25. So we conclude that the first sale, this is not large equilibrium. This is also not large equilibrium as well. Given that A stay out, do not enter the market, and B will certainly deviate from cut price to no cut price, because deviation will increase its payoff from 20, its profit from 20 to 50. Let's check whether this sale is a large equilibrium or not. So if given that A stay out, will B deviate from not cut to cut? No, because deviation will decrease the profit from 50 to 20. Okay. Given B not cutting price, will A deviate from stay out to entry? Yes, because deviation will increase the payoff from 0, its profit from 0 to 25. So this sale is indeed not a large equilibrium. Okay, let's check this sale, whether this is large equilibrium. Given A enter, the market will B deviate from not cutting price to cutting price? No, deviation will decrease profit from 25 to 10. Okay. Given B not cutting price, will A deviate from entering market to staying out? No, deviation will decrease the payoff from 25 to 0. So indeed, this is a large equilibrium. So not cut price and entry is the large equilibrium, is the unique large equilibrium in these entry games. So for our purpose, we always assume there's complete information. Everybody knows everything. Everybody knows that everybody knows everything, so on and so forth. However, in reality, we can have incomplete information. We can have asymmetric information. Some people know something that the other players do not know. So if such kind of asymmetric information and we do not have a strategic interaction among players, typically we end up in having two issues for the market. One is called adverse selections. An example would be second-hand car market. I want to sell my second-hand car, and you want to purchase a car, but clearly I have more information about my car than you do, and you are gonna think you are smart. You're gonna think that I will take advantage of this this asymmetric information. So you will walk away from the transactions. In such a situation, there's a mutually beneficial transactions that cannot be realized, and we call this problem asymmetric. We call these problems adverse selections. To solve these adverse selections, we can use a number of techniques to solve these adverse selection problems. For example, like screening, like signaling. So I won't talk in details about this sense. The second possible problems due to this asymmetric information is called moral hazard. A typical example here is insurance. So I get insurance for my new cars, and I'm going to think that because I get an insurance, my car is insured, I won't drive my cars as carefully as if I don't have insurance. And this behavior is called moral hazard. In the end, because of this moral hazard, it's likely that you won't get 100% insured. So if we have asymmetric information and where agents where players they have strategic interaction among them, we can analyze such kind of situation using what is called Bayesian large equivalence. But we will not talk about this.